Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for the BSc Physical Sciences students for the paper on Applied Electronics. I have been introducing to you the vector atom model. Now, this lecture is in continuation with what we have been seeing so far with regard to the Bohr-Sommerfeld atom models and the introduction to the vector atom model. Hence, the contents are space quantization and allowed orientations, orbital magnetic moment, the concept of spin and spin magnetic moment. I told you in the last lecture, the 2 Dutch scientists Uhlenbeck and Goudsmit, they thought that to explain some of the experimental observations which otherwise could not be explained by the Bohr atom model as well as the Sommerfeld model. I told you that Sommerfeld introduced the ideas of relativity in atomic physics. In spite of all these things, one could not explain the Zeeman effect and the Stark effect. I told you the Zeeman effect, the splitting of the spectral lines and the application of the magnetic field, the Stark effect, the splitting of the spectral lines and the application of the external electric field. These things, along with the fact that the fine structure of H alpha line, as I told you some time back, those things they remain unexplained, which led to the vector atom model. The vector atom model rests on 2 important concepts, namely space quantization and the introduction of electron spin. As I told you just now, the Dutch people, physicists, they thought of spin because Earth is revolving around the Sun. Apart from the revolution, right, the rotation of the Earth or the planets, they are also spinning. So, the concept of spin which was introduced for the electrons in atoms came from the Dutch scientists Uhlenbeck and Goudsmit. Therefore, the 2 key features that you have in the vector atom model are space quantization of the electron orbitals and the spin. What is meant by space quantization? Now, you know, you have heard of quantum theory, the energy of the photons are discrete, or you know the particle in a box problem, or we have seen the Bohr atom model where the energies are discrete or quantized, right. That is the reason quantum theory means the energies are quantized or momentum they are quantized and so on. So, what is meant by space quantization? in the Bohr atom model, we say the electron is revolving in an orbit, right. What is orbit? The orbit is this. The electron can also revolve like this. So, the electron can revolve like this. You assume a sphere, right. You assume a sphere, not a circle. The electron can revolve along the circumference of the sphere. You got a sphere, right. You got an electron and a proton here, the electron is here. The orbit can be like this, the orbit can be like this, the orbit can be in this orientation, orbit can be in this orientation. All possible orientations are permitted. I hope you understand. In the Bohr atom model, there is no restriction with regard to the orientation of the orbits. The electron is revolving in a circular orbit. The circle can be any circle. It can have all possible orientations starting from 0 degree to 360 degrees, right. The electron in principle is revolving along the circumference of a sphere. All possible orientations are allowed, but now we are going to quantize the orbital planes. The electron, unlike the Bohr atom model, we are going to have only certain specific orbits or certain specific orientations. I will show you now. The electron can revolve only in certain specific orientations. Okay. You see here the electron is revolving, okay, like this. You got the electron revolving in an orbit like this, right. The electron can revolve an orbit like this, right. So, this orbit, it is vertical, right. This is inclined, this is horizontal, right. This is perfectly horizontal, this orbit is horizontal, this is inclined, this is also inclined. So, how many orientations are there? So, this is horizontal orientation, the vertical orientation, there are two other orientations. So, now in the picture, this is an elementary picture, that is to show space quantization. The electron in question can have 4 possible orientations. It can either revolve along this circle, this is a circle, right. They are all circles like the Bohr atom model. The electron is revolving in a circle and this orientation is perpendicular, this orientation is horizontal, this is inclined, this is also inclined with at a particular angle. So, now you should not ask the question, I suppose in this orientation with respect to this perpendicular, this orientation is some 40 degrees, right, or 45 degrees, the orientation may be 45. Now, can I have an electron with orientation 60 degrees? It is not possible. This shows only 4 possible orientations. So, this orientation makes 45 degrees. This orientation also will make 45 degrees. Now, therefore, only the electrons can revolve only in certain specific orientations. So, this is called a space quantization. In the Bohr atom model, there is no space quantization. The electron can revolve in all possible orientations, as I told you, starting from 0 degree to 360 degrees. You can have the electron revolving like this, 90 degree electron can revolve like this, or any other angle. All possible angles are allowed, but now it can revolve only in certain specific orbits having specific orientation or specific angles which the planes can make. You can have a orientation like this, electron can revolve like this, right. The electron can go in this horizontal plane or vertical plane or inclined and inclined. Okay. There are only 4 as is shown in the diagram, or it can have 6. Definitely there should be only restricted orientation. You can have only restricted planes, right, in which the electron can be found. So, I hope you understand. So, the electron can revolve only in restricted planes. The planes are restricted, the planes are quantized. So, in space the electron cannot revolve in any angle of inclination. All possible angles of inclination are not allowed. So, the space is quantized. In space, the electron can be found only in certain specific orbits or having specific orientations, right. This is called the space quantization. I will come back again, the space quantization. So, according to Sommerfeld, the electron moves in elliptical orbitals which are quantized as regard to their magnitude and shape, that the electron possesses 2 degrees of freedom, hence 2 quantum numbers n and k. That is what I told you in the Sommerfeld model. Description of electron motion in terms of these 2 quantum numbers implies that the electron motion is confined to a single plane. As an atom is a 3-dimensional entity, the orbital plane of an electron may take different orientations inside the atom. Classically speaking, the electron orbit may orient in all probable directions in space. That is a Bohr atom model. All orientations are allowed. Sommerfeld extended the concept of quantization, the space quantization, to the orientation of the electron orbits in space. According to Sommerfeld, out of possible infinite orientations, infinite means what? All possible degrees of inclination from 0 to 360, only certain discrete orientations are allowed for the electron orbits. This is one particular orbit, right. The space is quantized, that means the electron can revolve like this in this plane. If it revolves in this plane, the angular momentum vector will be in this direction, perpendicular to the angular momentum will be perpendicular to the plane of the orbit. This is the orbit, right. This is the plane of orbit. So, perpendicular to the plane of the orbit, you will be having the angular momentum. So, because the angles are quantized, the planes are quantized, that means the angles are quantized, right. It can have only certain inclinations. Certain inclinations means the angle will have certain values. So, the angles are now discrete. So, because the angle is discrete, the angular momentum vector also will become discrete. You will see the orbital angular momentum will take only discrete values, because of the fact that the plane is having discrete orientation. Therefore, the angle becomes discrete. Now, what are the possible discrete angles? The angular momentum, the orbital angular momentum will also become discrete. Let me not go to the spin as of now. I am talking about the orbital angular momentum, the electron, what is the velocity? The velocity is discrete, the momentum is discrete. So, now I am talking about orbital angular momentum, right. If the orbital angular momentum is along this direction, the electron being a charged particle, then it will have a magnetic moment, that is called the orbital magnetic moment. I will come to the orbital magnetic moment possessed by the electron, because it is revolving, that it will have an orbital magnetic moment. The direction of the orbital magnetic moment will be exactly in this direction, right. It will be a negative of this direction. The angular momentum will be in this direction, the magnetic moment will be in the opposite direction. I will come to the magnetic moment later. Now, we will confine our attention to the magnitudes that the theta will have or the orbital angular momentum will have. We are going to define magnetic orbital quantum number. Before magnetic orbital quantum number, we will define orbital quantum numbers, right. So, the vector atom model which we will be having here, when the electron is at this point travelling with a velocity u, the linear velocity. So, the momentum PL, L refers to the orbital angular momentum. Hereafter, I will be using this L. What is L? L is called the orbital quantum number. So, like the principal quantum number we had in the Bohr atom model, the n will stay. When the electron is in the first shell, n is 1, that will stay. Then, in addition to the principal quantum number, we will have what is called the orbital quantum number, that will be designated by L. So, we have in the vector atom model the orbital quantum number L. We will have a break at this point when we are discussing about the orbital quantum number. welcome back after the break. We have, in addition to the principal quantum number we had in the Bohr atom model, we will be having what is called the orbital quantum number L. You got L here as the suffix, because and this orbital angular momentum will be quantized, as I told you, because the discrete orientations which the electrons will take, the planes are restricted, the angles are restricted, and the orbital angular momentum will have discrete values. So, now on I will be talking about the magnitude of the orbital angular momentum, right. Because the orientation of the orbits are restricted, the angular momentum, orbital angular momentum, as I told you, is denoted by P suffix L. L will take values like 0, 1, 2, etc. I will come to those values later. So, P refers to the momentum, as is the usual case. L refers to the orbital quantum number. Okay. The direction of the orbital momentum I showed you in the previous picture. We require a reference direction, because when we are talking about orbital angular momentum, I told you that the momentum is in this direction. We demand a direction. How do you get the direction? You assume that you are applying a magnetic field, and I want to have the atom under the, not under the application of any external field. Therefore, let me assume that you apply a magnetic field and reduce the field to a 0 value. So, the applied magnetic field, which is whose magnitude is almost 0, that serves as a direction. This is the direction of the magnetic field, right. This is the direction of the magnetic field. Okay. Why do you apply the magnetic field? You apply the magnetic field because you need a direction. So, we require a reference direction with respect to which the orientations can be thought of, can be defined. Such a reference direction may be obtained by imagining the atom to be under the application of an external magnetic field B, whose strength is made to become almost 0. It will not disturb the electron orbits, it is almost 0. Then the magnetic field direction serves as a reference direction, right. Generally, the magnetic field acting along Z direction is taken as the reference direction. According to Sommerfeld, the vector PL can orient itself in certain discrete directions relative to the external magnetic field direction. This is known as quantization of direction or space quantization. As I told you, the orbit, you can have an electron revolving in this orbit, then I can have an orbit like this, then I can have an orbit, I can have an orbit. So, if you have got applied magnetic field Z along the Z, this is Z direction, you assume that this is the reference direction, you apply magnetic field almost 0 value, this is the reference direction. So, I have an orbit which makes, suppose the electron is revolving in this orbit, this is a reference direction. What is the angle made? Angle made is 90 degrees, right. Okay. Supposing the electron is revolving in this orbit, the field is also in this direction, the angle made is 0, because both are parallel, right. They are perpendicular, means the angle is 90 degrees. They may be 45, there may be another plane at another angle 45 degrees or 60 degrees. Therefore, the orbits can be found, the electrons can be found in certain specific orbits which make an angle of inclination with respect to the magnetic field direction. It may be 0 or 90 or 45 and so on. Okay. Thus, in the vector atom model, the orbits are quantized in magnitude, shape and direction. The space quantization of an electron orbit is specified by the projection of the orbital angular momentum onto the reference direction, such projections being themselves quantized. So, this is a picture in which you get at the quantified values that the orbital angular momentum which can be assumed by the electron. The electron can be found supposing with only certain definite orbital angular momentum. In the vector atom model, the orbital angular momentum of the electron is given by LH cross. What is H cross or H bar? H bar is the unit of angular momentum. You go to a shop and ask for the price of something, it is 10 rupees. So, similarly here the PL is the orbital angular momentum, it is PL, L is the value of the orbit. So, the L is I told you the orbital quantum number. So, many times L times H bar, but H bar is the unit of angular momentum, H bar is the unit of angular momentum, right. Therefore, what is B? B gives the direction, okay, and you have got orbits, okay, in this direction. Supposing you have got orbit in this direction, right. I showed you the orbital planes, right. I showed you the planes in which the electrons can be revolving, okay. The very many orbits are there. This orbit for the magnetic field is along this direction. So, if your magnetic field is along this direction, the angle made is 90 degrees, and when the angle made is 90 degrees, then 90 degrees, then L will be 0, ML is called the magnetic orbital quantum number, and ML will take 2L plus 1 values. If L is 3, ML will take, ML is called the magnetic orbital quantum number, ML will take 3 values, ML will take 2L plus 1 values starting from plus 3 to minus 3, plus 3 to minus 3. So, with regard to the orbital angular momentum, that will PL will be equal to LH cross, right. According to the concept of space quantization, PL can take only such orientation in space for which its component in the field direction B will take integral values of H bar. The momenta that can be assigned to the electrons will be in terms of L, and thus PL cos theta is quantized and given by PL cos theta equal to ML into H bar, and ML is called the orbital magnetic quantum number, and theta is the angle between PL and the field direction in space. The largest component of PL along the field direction is LH cross when ML is equal to 1. So, the value is less than the magnetic of PL, which means that the vector PL cannot align in the direction of the magnetic field. The angle between PL and Z axis is cos theta is equal to ML into H bar by LH bar ML by L. So, the point I want to tell you is the magnetic orbital quantum number ML will take 2L plus 1 values. ML is called the magnetic orbital quantum number that will take 2L plus 1 values starting from plus L to minus L. There are 2L plus 1 values. I showed you just now, when you have a applied magnetic field, if you are talking about the L is equal to 3 state, L is equal to 3 means what? L is, I will come to the details later. If you have L is the so called orbital quantum number. So, if you have an electron in the state for which L is equal to 3, then ML will take 2L plus 1 values. There should be integers, they are quantized, they cannot be fractions. Therefore, ML will 2L plus 1 means what? L is 2 means how much is 2 ML plus 2L plus 1? 2L plus 1 is 5. Now, here 3 means 2L plus 1, L is 3, 2 into 3, 6 plus 1, 7 values. So, what are 7 values? Plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3. Okay. So, 1, 2, 3, 4, 5, 6, 7 values, right. Therefore, for a given L value, ML will take 2L plus 1 possible values or 2L plus 1 possible orientations. So, the possible 2L plus 1 values are starting with L, L minus 1, L minus 2. If it is 3 means 3 minus 1, 2. That is what I showed you, right? 2, then minus 1, you got 3, 3 minus 2, that is 1, minus 1, minus 2, and up to minus 3. Okay. Now, that is what I showed you for 3, right? 3 you have 2, 1, 0, you have 3, 2, 1, 0, minus 1, minus 2, minus 3. They are ml values, right? Therefore, ml will take values starting from plus L to minus L, including 0, and this L is another quantum number. I told you in the beginning, apart from n in the vector atom model, L will be the quantum number called the orbital quantum number. According to Bohr-Sommerfeld theory, in the absence of external field, the energy of electron in the orbits for all orientations of PL in space. However, when with reference to the applied field, the energy of electron will depend upon the relative orientation of PL with respect to the field direction. Now, the electron motion is visualized as 3-dimensional motion. Space quantization therefore requires 3 different quantum numbers n, l, ml. When you have a magnetic field, then there will be you got magnetic orbital quantum number ml. So, the energy of the electron now depends on all the 3 quantum numbers in the applied field. So, we had n, l and ml. ml is called the magnetic orbital quantum number, right. So, you have the orbital magnetic moment. As I told you, when you have got an electron revolving in an orbit, it will have an orbital momentum perpendicular to the plane of orbit. I told you some time back there will be an orbital magnetic moment downward. Momentum is in the upward direction, the magnetic moment will be in the downward direction. How do you explain the magnetism in an atom? Iron is magnetic, right. How do you explain the magnetic moment possessed by the iron atom? Because an electron revolving in an orbit is equivalent to a current, right. A charged particle revolving in an orbit is equivalent to a current. With a current, when you have a current flowing in a orbit, there will be a magnetic field, right. So, that is what is shown here, a current flowing in an orbit, there will be a magnetic field that gives rise to a magnetic moment. Therefore, you will be having the momentum and also the orbital magnetic moment. Let me now give a summary of the lecture delivered now. The orbital motion of the electron gives rise to orbital magnetic moment. Similarly, the spin motion leads to spin magnetic moment. Both the magnetic moments are to be summed up, they will be quantized. Now, we will pass on to the questions. The questions are: give the magnitude of the allowed orbital momenta. Then the last question is: what is meant by spin of the electrons? With this, we come to the end of the lecture. In the lectures to come, I will introduce more quantum numbers which will come into the picture in the vector atom model, and we will proceed with the Pauli exclusion principle and so on. Thank you.